So now the question asked here, teachers, we know the types of wavefronts, but then the question, most often question is this: what would be the source of light which would give you a spherical wavefront? Which is a source of light which would give you a cylindrical wavefront, and which is the one which will give you the plane wavefront? What are the sources? So now for that only I have taken the example of this bulb. So if you have a bulb, just place it in a lampshade. So do you get light of on all sides of that shade? In all directions, do we get it? Yes or no, teachers?
Yes, ma'am.
Yes. So now if I try to draw a sphere, see now this bulb is going to be in space, right?
Okay.
And when I try to draw some geometrical shape around it, right? So this is the bulb that I'm going to have. The source of light comes in all directions, right? All around it, I can get the light. And if I try to draw a geometrical shape around it, what kind of a shape am I going to get in space?
Spherical shape.
It will be a sphere, right? Where the points on that sphere, all the points on that sphere will be receiving light from this source, and the phase of all those waves. And here we are talking about wave optics, right? So we are going to treat light as a wave. So all the waves will be arriving at with a particular phase at all points on that sphere. And we call that as a spherical wavefront. So the source here is going to be point source. So if the source of light is a point source, then the type of wavefront that we are going to get from it is spherical wavefront. If it is a linear source, now what is the meaning of this linear source? Say your tube light. Say your tube light. Okay, hold the tube light vertically. Just hold the tube light vertically like this. Now, I'll be getting light in that also. So this is a tube light, right? This is a tube light. I hold it like this. I'll be getting light in all directions from this also. And if I try to draw a locus, I'll have layers of circles. Can you? Are you understanding that? I can draw one circle here for this point, then one more circle for a point over here, one more circle for a point over here. So I'll get that. And if I try to completely draw it into a three-dimensional shape, what is the kind of shape that I will get?
Cylindrical.
It will be a cylinder. So if you want a cylindrical wavefront, the type of source should be
vertical.
Something like this. And this we call it as linear source. And another example of your linear source is the slits that we will be using in the YDSC experiment, or the single slit diffraction experiment, and all that we have source. Right? We have that slit.
Ma'am, usually linear means we can take lengthwise, no, ma'am.
What, ma'am? What's that? I didn't get you.
Usually linear means we will take a lengthwise, ma'am.
Lengthwise. Okay, it's going to be lengthwise like this. And you try to draw the locus, you're always going to get a cylinder. And so the linear source means it is going to, you can place it this way also, no harm. It has a length.
Yes.
You got me? It has a length. You place it horizontally, you place it vertically, it doesn't matter.
But
it will have a length dimension. So we call it as a linear source. So if it is a linear source, then it is a cylindrical wavefront. What about plane wavefront? From where do I get this plane wavefront? Now, what I want you to see here is this. So suppose I'm going to take a point source, okay? So I'm having a point source, all right? And I know it is a spherical wavefront around it, right? It's going to be a spherical wavefront all the way. Now, as I keep increasing the distance from the source, what's happening here is the sphere is becoming larger and larger. Will you agree?
Yes, ma'am.
As I move away from the source, when I move off quite far, if it's going to be a very large distance, then what happens is these circles are so large, or the spheres are so large. If I'm standing somewhere here, only this part I will be receiving. Only this part of the spherical wavefront I will be receiving. Got me?
Yes.
That means I am receiving a part of that big sphere, which will appear like simply a straight line for me like that.
Flattened.
It's flattened. So I say now the wavefront is a plane wavefront. So which means the source of a plane wavefront is nothing but it can be a point source.
But
But then that point source is at a infinite distance from the observer, or from the point where we are, or it is at infinite distance from the point where the wavefront is received. So for a plane wavefront, if they ask you for the source, it is going to be a point source. Similarly, it could also be the cylindrical wavefront, which is again, I mean the linear source, which is again at a infinite distance from the position where the wavefront is received. So for plane wavefront, the source is going to be point source or linear source at infinity. So this is the very first question, or the very basic question asked in this lesson. What are the sources of spherical wavefront, cylindrical wavefront, and plane wavefront? So there is no source which straight away gives you a flattened or a plane wavefront. It is either the point source or the linear source, but the thing is they are at infinity. Yes, and I think you know about your, I don't have to discuss about the Huygens principle, but we should understand the Huygens principle very well to even draw all the diagrams with respect to reflection, refraction using Huygens principle. So should I go through that? I think that you should be able to do.
Yes, ma'am.
One another point that I want you to really concentrate here is this. This is the next question, important question that comes in our CBSE board again. What kind of, so I've just drawn for the, I'll just rub that off, okay? The type of wavefront that you will get when a plane wavefront is incident on a prism. So what does a prism do to any ray of light that falls on it? What phenomenon happens there? In a prism, what is the basic phenomenon? Refraction happens.
Refraction,
What is
yes.
refraction? What is refraction? Bending of light.
Light.
This we have learned. So now here with that idea, if we again here the idea used is again only Huygens principle. You use Huygens principle, and if you try to retrace the wavefront, if it is a plane wavefront, so this is a plane wavefront, ABC is a plane wavefront, we always draw it with a straight line because that is what we can do two-dimensionally, and that if it is going to travel and fall on this. So I would like to draw another line here to show you what exactly happens. So I'm going to draw a line here, teachers. So this is a plane wavefront, it's progressing, correct? According to my Huygens principle, it keeps progressing and say it is coming here. Now, if you see this point is here, take one more intermediate point here. You can have the direction of the wave drawn along that direction. It's going to fall here. Then it is going to bend. Similarly, this ray which is coming from here, it's going to travel a little larger distance from this plane wavefront, correct? And then be incident on the prism and then come out. So what is happening is here, this ray up there, that wave is traveling a larger distance outside the prism. This is traveling and it is already bent and it is going to come out. So if you try to follow their direction, this is going to be the locus of all those waves. So what is the shape that you're getting is a plane wavefront. So if they ask you the question, what is the shape of the wavefront or what type of wavefront is the refracted wavefront when a plane wavefront is incident on a prism? The answer is a plane wavefront. And the next thing that I will ask you here is what happens if a plane wavefront is falling on a concave mirror? So again here, this, remember all these red rays that have been drawn is the direction of the wavelets coming from the various points on the wavefront. So those waves are going to travel this way. This is going to be incident on the mirror first. So it will get reflected. So it will be somewhere here. Whereas this wave which is going, it is going to reach the mirror after some time, after this wave has reached. So it will take its own time to reflect. So when this, you could take this arrow mark that is there. This has come already here. This wave is only here and this wave is here. So if you try to draw the locus of that, you are getting a spherical wavefront, correct? The reflected wavefront is a spherical wavefront. So a plane wavefront becomes a spherical wavefront after reflection from a concave mirror. Similarly, this would have been given to you. This is all textbook examples which are given. You should extrapolate it to the other devices that you know. So now if I can just, I drew it for my children to understand. So now coming back here, again a plane wavefront that is incident on a convex lens. So you know it will converge the wavelets. So the kind of wavefront you're going to get is again a spherical wavefront. So through a convex, a plane becomes, after refraction through a lens, the plane wavefront becomes a convex, or it becomes a convergent wavefront or a spherical wavefront. Getting the idea?
Yes, ma'am.
Yeah. Then what would it be if it is a convex mirror? If it's a convex mirror, what would it be? How is it going to be? So see here, this is a plane wavefront. Your ABC is a plane wavefront. The wavelet from this is incident here. A little before or little after this wavefront has reached this point, correct? Correct? A wavelet, it's reaching this point, which is slightly behind this point. Will you agree?
Yes, ma'am.
And which is, again, this with respect to this point is slightly behind. So this wave is going to still keep traveling. But this wavelet from point B would have traveled and got reflected.
Yes.
So a particular time at that, this is still traveling. Whereas this has hit the mirror and it has started traveling back. It has started retracing backward. So what's happening here? This point will be here. The wavelet from this point B has, after reflection, will be somewhere here. And the wavelet from this will be somewhere here only. So if you try to draw the locus, that's our Huygens principle, right? Drawing the locus, the tangent, common tangent, we call it. That's the second part of the Huygens principle. When you draw the common tangent to all those points, it is going to be a curve, which means it is going to be a spherical wavefront. Is it convergent or divergent? How do I decide that? Is it convergent spherical wavefront or divergent spherical wavefront? See, the wavefront is increasing in its radius of curvature like that.
Diverging.
So it is diverging. And one way I make my children remember to draw is, see, convex mirror, if you draw like this, your reflected wavefront is also going to be parallel to that shape. Are you getting me?
Yes, ma'am.
So mirror and I mirror, if I draw it like this, sorry. So if I draw the mirror like this, after reflection also, I will, this is my wavelet that is falling, right? And after reflection, after some time, if I see, it is going to be. So draw your rays first. Teach your students to draw the divergent ray. After drawing the divergent ray, ask them to draw parallel curves to the mirror. So that will be the wavefront. So that way they will easily remember the way they have to draw the wavefront. That's how I teach them. Will that be fine? And the next type of wavefront that you should see in this, all these are 1-mark questions, teachers. They'll ask the teachers, they'll ask the students to draw the type of wavefront after refraction through a concave lens, convex mirror, concave mirror, prism. All these 5 will definitely be asked. One of them will definitely be asked. I mean, it's a very often asked question. So here you can understand this.
Yes,
so again, here the concave lens is divergent. So draw the ray. They know the ray diagram already. So ask them to draw the divergent ray diagram. Then draw the curves. So that will be the divergent wavefront again. Even in a concave lens, it's going to be a divergent wavefront. Fine. So that is the first part that I wanted to tell you all in this. Then of course about your Young's double slit experiment. What I wanted to touch upon is I'm not doing the derivation because the other day I think you all wanted more of the numerical part. So I'm just going into the final expression of the amplitude that you will get, the resultant amplitude after superposition principle. So should I go through how do you get this? Teachers, I want an idea from you. Should I derive? Not necessary, isn't it? You can go through the derivations. Yeah, not necessary. So we will just go through the final expression. So if it is your amplitude, the resultant amplitude by superposition principle is going to be a squared is equal to a1 squared plus a2 squared plus 2a1 a2 cos phi. Okay, fine. What is a1 here? This equation is written for what? Resultant amplitude of two waves superposes, right?
Yes, ma'am.
Two waves superpose on each other. This is the resultant amplitude. What is that a1 there? What is that a2 there? What is that phi there? What do you think is a1? What do you think is a2? What do you think is phi? A1 will be the amplitude of the first wave. Exactly.
A2 amplitude of the second
the other wave.
Phase difference.
It's a phase difference between the two waves. Right? Phase difference between the two waves. Fine. Okay. Now here, quick recall. The other day when we were doing waves, 11th lesson, did we give an equation or relation between phase difference and path difference? Do we know that? At this juncture, it's very important to recall that point. What is the relation, teachers? Phase difference
equal to 2 pi by lambda into pi.
I didn't get you, ma'am. What is the relation between phase difference? I did not hear you. Please, can you repeat it, ma'am?
Del is equal to 2 pi divided by lambda into pi.
Del phi. Phase difference is equal to 2 pi by lambda times
lambda
path difference.
Yes,
2 pi by lambda times path difference, right?
Yes.
So let us keep that in mind because that's a very helpful equation. So I'm giving that in your next slide here, right? And before that, this one. And before that, do we know this relation? We should tell the children about this relation. That is your intensity. How is intensity related to amplitude? Intensity of a wave. How is it related to the amplitude of a wave? How is it related? It is related this way.
Directly proportional to
I is proportional to a squared. So if I want to rewrite this equation that I've written, a squared is equal to a1 squared plus a2 squared plus 2a1 a2 cos phi. If I want to write that in terms of I, okay, intensity. So the equation becomes a squared will be replaced by I, correct?
Yes,
what will a1 squared be replaced by? So each wave will have its own intensity, isn't it? So that is why you start, teachers, I1. Then A2 squared will be I2. Then plus 2, A1, A2 it is. So it will be root of I1, I2 cos phi. So this is the general expression for the resultant intensity when two waves of different intensities superpose on each other. Superpose means they are going to meet each other, right? Now bring it down to your YDSC. What is YDSC? Young's double slit experiment. There, what are we actually doing is, we are having one point source. And then from that, the wavelets travel. And we have two slits, which are going to act as coherent sources, right?
Yes, ma'am.
And we know what are coherent sources. Now, what is the speciality of this Young's double slit experiment, or what do we do to this equation when it comes to Young's double slit experiment is, the intensity is the same. So we can very well write this I1 as some I naught. I2 also has I naught. I1 and I2 again can be written as I naught and I naught. Why? Because all the intensity will be the same because we are receiving it from the same source. So what will happen to this equation? When I do this, the equation, if I write it in terms of amplitude, it is simply going to be a squared is equal to a squared plus 2a squared cos phi. And when I pull out that 2a squared as common term, it's going to be 1 plus cos phi. These are all very important equations that we must remember for solving numericals. That's why I'm trying to recall the equations first, and then we will try to solve few questions. So now here I, so a squared will be replaced by I because I know I is proportional to a squared. Then I've written 1 plus cos phi. This a squared, I've written it as I naught. Why have I written as I naught? Because that is the intensity of the source. Are we clear?
Yes, ma'am.
Yeah. So I is equal to 2I naught into 1 plus cos phi. So this is one way of writing your resultant intensity for YDSE experiment. And here, when it is YDSE experiment, so I've given you the phase difference and path difference formula. Also, phase difference is 2 pi by lambda times path difference. Right now, in this, we have to discuss what is I. I maximum. When is I maximum here? This equation is there. When is I maximum there? What decides I maximum and I minimum from this equation? Teachers. In the equation, either decide one. Will I not change?
Phase angle.
Only phi can change. Phi between two waves can be different. Right?
Yes, ma'am.
Only phi between two waves can be different. I naught is, it's coming from the same source. So I naught cannot change. So I keep the I naught as such. Right? So the thing is, this term should be maximum. When will this term be maximum? We know any trigonometric functions, maximum value is plus 1. Right, teachers?
Cos
So when is
zero
cos?
value.
So cos phi should be plus 1 for this whole term to be maximum. So let us understand that cos phi is plus 1 means then this equation becomes 2I naught into 2. So the maximum intensity in a YDSE experiment is going to be 4 times I naught. One important point that I want you to note down. Here is that. When I say 4 I naught, what is this I naught? That's the important point I want you to note down, which will be very helpful for your numericals. When I write I max is 4 I naught, what is that I naught, teachers?
Density of the source.
Intensity of the source, the original source.
Yes, ma'am.
So if I can go back to this diagram here, idu I naught irundal. Okay. If I start with I naught here.
This is a very good picture I have here, isn't it? So water wave, and you are able to see the spherical wavefront. I think she is. So in 3-mark question, they may ask you the using Huygens principle, explain refraction and refraction of light. I think this is this all you must have done, no?
Yes.
From rarer to denser or denser to rarer.
Rarer.
This picture, I liked it very much. This picture. It's a wavefront incident. It's about refraction. So every point in the wavefront, as soon as wavefront touch every point in the wavefront, becomes a source of secondary wavelet, isn't it? And the tangential envelope. If you draw these are the green color denotes refracted wavefront. These are incident wavefront. So as soon as the wavefront touch, see now this part of the thing is touched first, isn't it? This part is touched first. So it starts propagating secondary wavelet. So this explained beautifully the propagation of the wave. in the form of secondary wavelets. This all ma'am touched upon it. So now whenever I explain this principle of superposition, I used to take one cork here. This is a cork. When two waves are approaching here, when they are in the, what is the phase difference between this pulse and this pulse? If you consider phase difference, they are in the same phase, no?
Yes, ma'am.
They are in the same phase. So now see the displacement of the cork. So this cork, you can consider this as a particle. This particle is subjected to two waves, two pulses, which are in the same phase. So now when the resultant amplitude, we take it as 2A, isn't it? When the phase is 0, A1 plus A2, it becomes A1 plus A2. So because we can write Y1 as A sin omega t, Y2 also as A sin omega t. So Y is equal to 2A sin omega t, isn't it? And the resultant amplitude will be 2A. So because they don't have any phase difference here. So suppose if you consider this two pulses which are in the opposite phase, the resultant amplitude is 0. The crest of one wave fall on the trough here. So the particle will not undergo any displacement. So this is about two slits, Young's double slit experiment. And we always draw this diagram, source 1 and source 2, how each source produce alternate crest and trough. And when they superimpose two lights, see, whenever I teach Young's double slit experiment, I ask the students, can light plus light, light plus light, what will happen when two light beams are superposing? Can they bring about darkness? Is it possible that you get darkness when light and light superpose, two light beams? Is it possible? See when if you have two bulbs, they will say it is not possible, no, because there are two sources of light. How you can expect darkness?
Coherent sources are
coherent source, yeah. But when you have a particular setup here, when you have a setup like Young's double slit experiment, where light beam is allowed to pass through two slits, okay, narrow slits. When they are allowed to pass through a narrow slit, it is possible. Light and light can result in darkness. Then you start explaining. So if you take two sources now, you have two sources of light. So propagate as crest and trough. When crest of one wave fall on the trough of the other, you get darkness. Whereas when crest and crest fall or trough and trough fall, all these are bright. And all these points where crest of one wave fall on the trough of other, you have darkness. So light and light can combine together to produce darkness. That is the basis of interference. The interference is the variation in the intensity of light. Variation in the intensity of light when two coherent sources superpose. That way only we define. So definitely we should explain to them through this diagram, because see here, if you have two sources S1 and S2, they can be derived from the same source. So when see here, I've drawn 7 waves here 9 waves. Okay, what is the path difference between them? What is the path difference? 2 lambda.
See, ma'am, sorry.
Yes.
I'm back. So I think we were in that maximum, right? I max and I minimum, right?
Yes,
One
yes, ma'am.
very important point that I wanted to drive home here is, this is what I was trying to tell you. When it is maximum, see, when the source's intensity is I0 in YDSE experiment, you will get the I maximum value as 4 times I0. Got it?
Yes, ma'am.
Okay. And when it is, if it is I minimum, it is going to become 0.
Zero.
Point that I want you to understand is, na I0 RN because I am telling you, I'm going to show you one problem in your textbook, or I'll try to tell you something there. When I start with I0 for the source, I max will be 4 times I0. You're getting that point? You're
Yes,
getting
ma'am.
that point? So now suppose in some of your exam questions, what happens is they tell you, let me get that question. If I can get that question, it will be very nice. 1 second. Okay. I'll discuss it on my own. I'm not finding it. I'll just do that. Okay. Let me take a slide here. So if I start with I naught, if I start with I
You
naught,
share screen, ma'am.
okay, screen is shared, right,
Yes,
people?
ma'am.
So if I start
Yes.
with I naught, my I max is 4 times I naught.
I not.
But in some of your board questions, what they will tell is in a YDSE experiment, the I max value is I naught. The maximum for constructive interference, the intensity is I naught. So what would be the source's intensity? Source I naught na, I max is 4 times I naught, correct?
Yes.
If I say source is I naught, if I say source is I naught, then not source is I naught. If I max is I naught, then what is the source's intensity? What is the source's intensity?
I naught by 4, ma'am.
I naught by 4. அது ஞாபகம் வச்சுக்கோங்க. புரியுதா?
Yes, ma'am.
Okay, because that's a very important point that we remember while solving such questions. I'll send such questions as an assignment to you, where they will say the maximum intensity or the intensity of constructive interference at a point is I naught. Okay, and they'll ask you to find certain things for that. But for that, you will need to know what is the source's intensity. What is the source's intensity? I naught by 4. Are we clear?
Yes, ma'am.
Yes.
Are we clear? And suppose
Yes,
as we come down, as I show you the questions, you will understand one place, you will understand this thing. Why am I asking you to know this I naught by 4? Upon and I calculate, they'll say, what would be the intensity at some other point? Got me? They might give you the phase difference or they might give you the path difference. So when that is there, I should understand that I must use the equation as, if I go to the intensity equation, I will use the intensity equation as this. That is, I will write now my new intensity equation as not I naught plus I naught. Are we clear? What will I write it as? See, earlier for YDSE, we wrote I is equal to I naught plus I naught, correct? Plus 2 root I naught into root I naught cos phi. Am I right, people?
Yes,
Are you getting
yes,
me?
Yes.
Are you getting
Yes,
me?
ma'am.
But now will I use the same I
Yes.
naught or what should I use? If I say your I max is I naught, what is your intensity of the source? I naught by 4.
I max, ma'am.
So I இல்ல என்னோட question புரியுதான்னு கேக்குறேன். இந்த I max வந்து I max I naught னு சொல்லிட்டேன் உங்களுக்கு. Okay? Somebody's thing, if you can mute yourself, please. See, I've told you I max is I naught. Okay? Then what is the source's intensity? I naught by 4. And the same I naught by 4 will come for the source S1 and S2, correct? Are you getting me, people? நான் சொல்றது புரியுதா இல்லையா?
Yes, ma'am. Yes, ma'am. Yes, ma'am.
Are you understanding? So இப்போ intensity வேற ஒரு இடத்துல நீ கண்டுபிடிக்கணும் அப்படிங்கும்போது I will take the intensity of the two sources as I naught by 4 and I naught by 4 and not I naught. Are we clear with this? இங்கேயும் I naught by 4 போடுவேன். நான் சொல்றது புரியுதா?
Clear, ma'am. Clear. Yes, ma'am.
Yeah?
Yes, ma'am.
So I'll write this also as I naught by 4. So that's a very important point that I always want to drive or tell children, that let us understand this point. So this will also be I naught by 4. This will also be I naught by 4. Now I can find out I if cos phi is given, correct?
Yes,
So let
ma'am.
me understand this one point, which will be very, very helpful for your problem solving. So when I give you some
IMAX.
today I'll try to post some assignment for you, okay, where such things are to be understood. So just
Yes,
try. I just wanted to tell you all this one point. What is the relation between Imax intensity and the source's intensity? So source I naught irnana, my Imax will be 4 times I naught. This is for YDSC. Got it? So if
Yes.
the Imax is whatever is the Imax value by 4 is the intensity of the sources that I used in the YDSC experiment. Paka?
Yes, ma'am.
Yes, ma'am.
Got it? Okay, good.
Sorry, ma'am.
So all these are what? All these are derivations that you do. Okay, so I'm not going through it. I'll send the PPT. Probably you could go through the PPT. Right? Okay. So this is another question. So I'm trying to get all the board questions for you. So this is another board question that comes your way always. If we use 2 sodium lamps illuminating 2 pinholes, we will not observe any interferent fringes. Why? So sodium lamp, is it monochromatic? Sodium
Yes,
na
ma'am.
or color dane.
Yes, ma'am. Monochromatic.
Monochromatic. Monochromatic.
So if you take 2 sodium lamps, both of them will give the same wavelength, correct?
Yes, ma'am.
Yes.
The light coming out of it will be the same wavelength. Will be the same frequency also. But will they behave as coherent sources? Because for YDSC, definitely we must have coherent sources, correct? Otherwise, we
noise
don't see
disturbance.
interference. We don't see interference if the sources are not coherent. Now, why are 2 separate sodium lamps? They are of the same wavelength, same frequency. Still, they cannot behave as coherent sources. Why? So when does any source give out light? What is light actually? What is
Radiation.
actually light? Electromagnetic wave, correct?
Radiation,
When
yes.
radiations. When do we get radiations? When will energy be given out? Atoms.
Particle
Or atoms.
moves from one energy level to another.
Exactly. So you will have to excite that atom to an excited state, and when it comes to a lower state, it will give out radiation, correct?
Yes,
This
ma'am.
we study in our atoms lesson, that when electron jumps from the higher excited state to the lower excited state, it gives out a photon. And if it is in the visible region, we are going to call it as light, right? So there should be some jumping of the atom from the excited state to the lower excited state or to the ground state for me to see those radiations. Now the point here is, if I have 2 sodium lamps which are going to give the same wavelength and frequency, all right, it is not necessarily going to make its atoms come to its lower state at the same time. Always. So the one lamp can give now, then it can wait, and after some time it can give out another wave. This one again can give it now, then after some other time that this has given, this can give out a wave, right? So what's going to happen is the phase between the 2 waves is not going to be a constant. The phase difference will not be a constant with respect to time. So if the phase difference is not constant with respect to time, my interference is not going to be observed. So now it will be bright, very next moment it might be dark. So I'm not going to get at the same point a bright constructive interference, or I'm not going to get destructive interference. Are you getting me? So that is a very reason for 2 independent monochromatic sources not behaving as a coherent source, as a pair of coherent sources. So that is what is given here. This is because of the fact that the light wave emitted from an ordinary source like sodium lamp undergoes abrupt phase changes in times of the order of 10 power minus 10 seconds. So abrupt phase changes. So it is not a constant phase change. Thus, the light waves coming out from the two independent sources of light will not have any fixed phase relationship and would be incoherent. So this is the point you should drive home for the children. They should say that the light coming out from the two independent sources will not have any fixed phase relationship. So this is the phrase that you must definitely make the children write. If the question is, why can't two independent monochromatic sources behave as a pair of coherent sources? So all small little 1 mark questions that you'll get in wave optics, where children will kind of struggle to answer suddenly given the question. So are we clear with this, teachers?
Yes, ma'am. Clear,
Fine.
ma'am.
Okay, fine. Then the next thing that I wanted to discuss here is about the, see this nth bright fringe position we know, then we know the bandwidth. Do we know the bandwidth formula also? And have you done, this is a fringe width, and have you done the angular width and linear width? So this is another important point for you in this lesson. Talking about angular width and linear width of the fringes. Linear width, na, it is simply the fringe width or the bandwidth. So do we know the expression for fringe width? What is beta equal to? Teachers. This is beta. Beta is equal to lambda d by
Lambda
d.
d by
D by
Lambda
D.
d by d. And here one more point that you should, one more learning point or very often asked question in your 1 mark or it might be even a 2 mark question. What they ask you is they'll give you the fringe within air or vacuum. And they'll ask you what is the fringe, what happens to the interference pattern if something is changed. So now if beta is lambda d by d, depends on 3 physical quantities, right? Namely the wavelength of the light used, the D, capital D is the distance between the slits and the screen, and small d is the distance between the two slits of the YDSA experiment. So this is our YDSA experiment. So we know beta depends on lambda, it depends on d, it depends on small d also. And how exactly it depends on the lambda increase ana, beta will increase. D increase ana, beta will increase. Small d increases, beta will decrease because it is inversely proportional. All this we know, right? Now the question would be, what happens if D, all this we'll be able to easily explain. Suppose the question is, this whole interference experiment is done underwater. So full setup, you're going to keep it in water. Generally, we keep it in air, right? Lab means the surrounding is air. So any light devices that we use, it is always done in air. Lens, now where am I placing? In air. So what is the medium surrounding it? Air. So all that unsaid when we are discussing all these experiments, they are all done in air, right? The surrounding medium is air. What happens if the surrounding is not air? So I take the whole Young's double slit experiment underwater. So if I take it underwater, will the fringe width change? So now I have to see again at beta, what are the physical quantities? Now, set up small d and capital D are not going to change. What will lambda change? Does the wavelength of light change when it enters from one medium into another? Does the wavelength change? What are the physical quantities that change when light travels from one medium into another medium? Any wave, you can associate frequency, you can associate wavelength, you can associate speed. These are the 3 physical quantities that you will associate with any wave, basically. So of these 3 quantities, namely wavelength, frequency, and speed, frequency will not change. Why frequency will not change? Because it is a property of the source. So na bulb mela vechalum onada, tannikulla vechalum, it's going to give only that particular wavelength, that particular color. So it is going to give me only that particular frequency. What is frequency when it comes to waves? It is a number of waves that the source will give out in 1 second. That's how we define frequency. So if I want to say frequency is that, na bulb mela vechalum seri, tannikulla vechalum seri, The number of waves given out by the bulb is not going to change. Is it going to change? No. So frequency is a property of the source, so it will not change. But what about wavelength and speed? Definitely they will change. That's how refraction happens. So lambda is going to change. Will lambda decrease or increase? Aditya, you have to recall their formula in the 10th standard that they learn. If a beta in a medium, I have to write it as lambda m into d by d. But how is this lambda m related to lambda a? Lambda m is lambda a by this small n that I've written. That small n is nothing but refractive index of that medium. The new wavelength is going to be lambda a d by d. What is this lambda a d by d? It is beta a. So make them remember this formula. Very important for you. The next important concept question that you will be asked is what happens to the interference pattern? So what happens to the interference pattern? Now, how will you answer? When I say interference pattern, it should talk about what is happening to the fringe width. Is it becoming lesser? Is it increasing? What will happen to the fringe width? Accordingly, you will say the interference pattern is becoming narrow or the interference pattern is becoming broader. What decides that? The fringe width. And what decides the fringe width? This formula. So the fringe width in a medium is 1 by n times the fringe width in air. Right? And beta m will always be less than beta a because your n is always greater than 1. Because refractive index of any other medium other than air is more than 1 always. So beta m is always going to be less than beta a. So if beta m is less than beta a, what is happening to the fringe width? Is it contracting or is it becoming broader? Beta m, it is the width of the each fringe that is going to keep reducing. So if it is going to go on reducing, what actually is happening to the fringe pattern? The fringe pattern narrows down. Fringe pattern narrows down. Now here I wanted to show you one particular question from the textbook. So just give me a minute. Right. So the 10.4 example. What is the effect on the interference fringes in a Young's double slit experiment due to each of the following operations? So this is what I was trying to talk to you. First one is the screen is moved away from the plane of the slits. Very easy. What do you think happens? Screen is moved away now. Which one is changing? Capital D or small d or lambda or
Capital D.
capital D. So if capital D is increasing, what happens to beta?
Beta also increase.
Beta also increases. Okay. So what will happen to the interference pattern? Now you are tempted to say it will broaden. Correct?
Yes, ma'am.
It will broaden. Okay. I am not going to the next page. First we will discuss here, then I'll show you some answers there. Then the next question asked is the monochromatic source is replaced by another monochromatic source of shorter wavelength. So lambda is getting reduced. So what will happen to beta? Beta will
Also reduce.
It will also reduce. Very simple, right?
Yes.
Fine. Next one, it says the separation between the two slits is increased. So that means it is this small d. So if small d is increased, beta is going to decrease.
Reduce.
Very clear. The next one says the source slit is moved closer to the double slit plane. So source slit na another. You are having a source and from that light comes and it makes S1 and S2 as the two coherent sources. So that is the source we are talking about. S is what we are talking about. So what happens if that is moved closer? Now, do we have anything in the formula to tell us that?
No.
Are you getting me, teachers? So source slit means when if you take this diagram, though in the source slit, in the light in the rend S1, S2 mela vidande, and these two S1 and S2 are acting as coherent sources, correct?
Yes.
Yes, ma'am.
Giving you the interference pattern. Now, what the question says is you're going to move this S closer to S1 and S2. So is this distance involved in the formula?
No, ma'am.
It is not involved in the formula. Then how do I discuss this question? How do I discuss this question? This question. How do I discuss this question? So that is something else also involved there, right? Then next question, you see the width of the source slit is increased. So source slit nale edu in the S. Priyada. So idoda width increase ana. Is that width included in my formula here? In fringe width? No. So how do I explain that? So there should be something else also involved here. So we'll see that now. Okay.
Yes.
Then the last part says the monochromatic source is replaced by a source of white light. This is easy. Monochromatic source is replaced. Now I'll see colored fringes. Right? There also one small twist is there. So now we will go to the answers for all these 5 which are given in the next page. What is given there? See, angular, now they are discussing even angular separation here. Okay, let us talk about the linear beta first, then we will see what this angular separation is. Okay, wow. Now for all these, what is saying? See the B part, the separation of fringes, that is decreases. See, however, the condition mentioned in D. See, first 3 you are very easily able to answer because you had a formula to answer those 3 questions. But 4th and 5th, you said there is nothing in the formula for me to explain. So this condition, people, this too you must discuss. We are not giving the proof of it. We are not giving the proof of it. But then this condition must be satisfied for you to see interference fringes. So I have highlighted that. It says small s by capital S should be less than lambda by D. What is that small s? It is the slit size of the source slit. What is capital S? It is the distance between the source slit and the 2 slits of the YDSC. So now do we get an idea? So what you have to explain actually, see, they would have told you, see, however, the condition mentioned in D below. Why? Because in the examination, yes, what you will have to write is the separation between the 2 slits is increased. That is, this D is increased, fringe width will decrease. But then you will be able to see the decrease of the narrow fringe pattern only till this condition is satisfied. And a small d lambda by d will change. And what is the condition? S by S should be less than lambda by d. Only then interference patterns will be seen. So if you cannot simply change d to any value and say interference will be seen. Are we understanding this? So when the children write the answer, the separation of the fringes decreases provided which condition is satisfied? Provided this S by S is less than lambda by D is satisfied, where small s is size of the source, that is the slit size that we were talking in the C. See, they said no, the source slit is moved closer, na capital S is changing. Width of the source slit is changed, na small s is changing. Are we clear with this, teachers? Sorry, children never. Are we clear with this, teachers? Yeah. So what you must make the children write is separation of the fringes decreases provided this condition is satisfied. Similarly, separation of the fringes decreases provided this. So for every change, this condition must be satisfied. Then only it is fine. Are we clear? Are they first question? First question it is capital D, right? Capital D is not involved in this. So I don't have to talk about this condition for the first part. So just teach your children or revise with your children that this should be mentioned when they are giving the fringe width changing, provided this condition is satisfied in the will. Are we clear? And the last part, see, last part is when the monochromatic light is changed to white light. What happens to the fringes? You will get a colored fringe, and the center one will be a white fringe. What will be the next fringe after the white fringe? So the white fringe is here. what would be the next bright fringe that you see, up or down? So this is the central bright fringe that you see. So what will be the fringe above? What color will it be above and immediately below this? What color do you think it will be?
Violet.
What color do you think you're going to see? In a
Violet.
Vijay or colors varum. Vijay or
Yes,
colors
ma'am.
varum.
Violet.
Okay, so why violet? See, violet is not, see here, even in the question is given you only blue color.
Blue.
Now, why is he left out violet? Why do you think he has left out violet? Why he says only blue, then he talks about right? Why generally violet is never spoken about? Now, violet is not very sensitive to our eye. Blue is very sensitive to the eye. Okay, so you can talk with blue color. So blue color will be appearing first, than the red color. Got it?
Yes, ma'am.
Let's see
Yes,
here.
ma'am. Yes,
Are you
ma'am.
getting that? So be very clear about what is happening here. So this is a very important board question. So you are asking for board questions, right? Very important board questions. And one more very important board question is coming up now in diffractional. I'll tell you, right? So we will go back to our PPT now. So hopefully you got this. Then one more point that they very often asked is all about the angular width. So how do I write my angular width? How do I measure my angular width? Which is that angular width? Which is that angular width, teachers? See, I am getting a central bright fringe, right? Central bright fringe தானே. அதுக்கப்புறம் என்ன fringe வரும் இங்க? இங்க என்ன fringe வரும்? Dark fringe. Only then again I'll get my bright fringe, right? So from the dark fringe, if you draw a line to the center between the two slits, then draw this. These two lines will be making an angle, isn't it? That angle is what we define as angular width. Okay, wow. Got it? Now, how do I calculate that angular width? I calculate this theta first. Idu theta na iduvum theta. How do I calculate that theta? I take tan theta. What is tan theta, teachers? Opposite by adjacent. Tan theta is opposite by adjacent. Are we clear?
Yes, ma'am.
Yeah, fine. Now, this fringe width is beta, isn't it? This distance will be half of beta. So opposite side is beta by 2. And what is adjacent side? D. So my theta is beta by 2d. But what I want is 2 theta. What is that 2 theta? That is what I call it as the angular
Theta by-
width. That is what I call it as the angular width. So what is angular width? Beta by capital D. Are we clear? And what is this beta? I know it is lambda d by small d.
That is it.
So d and d will get cancelled. So the angular width is actually lambda by small d. Now based on this, you can discuss about your angular width. What happens to angular width if the capital D is changed? Nothing happens to it because it is independent of capital D. Right? What happens if lambda is changed? You can discuss. What happens if small d is changed? You can discuss. But then here also, remember the condition S by S should be less than lambda by d for you to actually see the interference pattern. So whatever happens till that condition is satisfied till you're able to see the interference. If that condition stops getting satisfied, you don't talk about interference pattern at all. So just keep this in mind. So this is angular width, which is lambda by d, which is independent of d. Is it fine? So this is the next point. All are small little questions that you will get in this lesson. These are all 1 marks where children generally lose. So I always try to discuss this point. So are we clear?
Yes, ma'am.
Yes, teachers. Okay, good. Now we are coming to a few problems now, which you are waiting for. And because of my in-between thing, I thought really, I'm sorry that I couldn't discuss many of the questions. But these are all simple for you. Yeah? And see this one, 2 plane monochromatic source waves propagating in the same direction with amplitude A and 2A and differing in phase by pi by 3 radians, superpose, calculate the amplitude of the resultant wave. Somebody's thing is, please help now. Thank you. So A1 is A, A2 is 2A, phi is pi by 3. This is very simple, right? But this is a CBSE sample question. So anything simple and easy also can sometimes come. So let's not avoid that. The next one, if you see two sources of intensity, I and 4I are used in an interference experiment. Find the intensity at points where the waves from two sources superimpose with a phase difference of 0, pi by 2 and pi. I think this is also simple. Nothing great about it. Should I discuss? So this is the formula. I1 is I, I2 is 4I, right? And get your answer. Is that fine? Is that fine? And this is the one which I wanted you to really see. See, it says in a Young's double slit experiment, this is your textbook question, very much your textbook question, but a very important CBSE board question. So what it says in a Young's double slit experiment, the intensity of light at a point on the screen where the path difference is lambda is k units. Find the intensity at the point where the path difference is lambda by 4, lambda by 3, lambda by 2. So path difference கொடுத்தா நீங்க என்ன கண்டுபிடிக்கலாம்? ரெண்டு waves path difference கொடுத்தா what can you find? Because if you want intensity, you want phi, correct? In the formula of intensity, you have phi. You want that phi. That phi is the phase difference. How do I find out phase difference? I know the formula for or the relation between path difference and phase difference. What is the relation between path difference and phase difference? It is this. That is your
Pi divided by lambda.
exactly path your phase difference generally we write as that phi is the phase difference. That is 2 pi by lambda times path difference. This path difference only is being given to you as lambda by 4 or lambda by 3 or lambda by 2. So can I go substitute that there and get my phi?
Yes,
And once I get my
by
phi, I can, once I get my phi, I can very well go find out my intensity using the formula. I is I1 plus I2 plus 2.
Anuja
I1,
ma'am,
I2
Anuja ma'am,
plus
please
5.
mute your mic. Anuja ma'am, I think noise is coming from Anuja
Yeah,
ma'am mic. Yeah.
She wants to answer, but then the moment she
but,
unmutes, some technical
some noise is
glitch
coming,
there.
yes.
Some noise is coming. So now here you can use your formula I1 plus I2 plus 2 I1 I2 root under root cos phi. We have found out phi for each thing, go substitute it and get your answer. And if it is YDSE, remember your I1 is going to be equal to I2. It is going to be written as I0. So I can very well go do that and get my answer. Are we clear? And when you see this answer here, teachers, you get this as 4 I0. See, you started with I0, you're getting your I as 4 I0, which is maximum, right? Yes or no? And that has been given in your question. That has been given in your question as K. What they are saying is in a double slit experiment, the interference of light at a point on the screen where the path difference is lambda is K. So when the path difference is n lambda, you're getting constructive interference. Yes or no? And in that case, it will be I max. At all those points, it is I max. So whatever is the maximum intensity you're getting, so let me go there. So whatever is the maximum intensity you're getting is 4 I0, correct? Yes or no? So this 4 I0 is actually K. Then once you get your I in terms of I0, you know 4 I0 is K. So 2 I0 will be what? K by 2. Similarly, if you get 4 simply I0, what is I0? It will be K by 4. So they are asking you to express it in terms of K, a very often asked question, teachers. So hopefully you have understood this part. Fine?
Yes, ma'am.
Yeah? Then see
Yes.
this one. This is also easy, right? Phase difference has been given. You've been asked to find out the intensity ratio. So this is very simple. And see, it is simple, but then see the thing, it is a CBSE question. So such questions you can expect this year also because of the COVID. I'm hoping some of it will happen like that. So let us see. So again, this is also the same thing. So I'm just skipping that. This is again a very often asked question. Hopefully my PPT is visible to all of you. This is two coherent sources whose intensity ratio is 81:1 and produce interference fringes. Calculate the ratio of intensity of maxima and minima in the interference pattern. So this is I1 by I2 is 81/1. Okay. And let us understand this I max. And they've told you this is intensity is in the ratio 81:1. And I know the relation between intensity and amplitude as this. Intensity is proportional to amplitude square. So A1 by A2 will be root of 81/1, 9/1. So this much I know. But I also know I max as, see, I max is A1 plus A2 the whole square. Correct? But A1, A2 taniya illa. So what I can do here is divide this equation by A2 say throughout. Then this will become A1 by A2, the first term. Next term will become 1. Are we getting this? And then the A1 by A2 I know is 9, correct? So I can rewrite this equation for I max as A1 plus A2 the whole squared as, are you getting me, teachers? I can write,
Yes, ma'am. Yes, ma'am.
yeah, I'm getting this I max can be written as A1 by A2 plus 1 the whole square. Can I write it this way? And I know already A1 by A2. A1 by A2 is 9. So if I simply go substitute that, I'll be able to get my I max. Similarly, I minimum will be A1 by A2 minus 1 the whole square. So if I can calculate that, I can easily calculate I max by I min. Very often asked board question again.